So hello everyone, welcome to lecture number 6 of VLSI Physical Design with Timing Analysis. Today we are going to discuss about various graph searching algorithms which are useful in VLSI Physical Design. So the following are the contents of today's topic. We'll be dealing with the two graph search algorithms. First is depth first search, or we can call it as DFS, and the next one is breadth first search, which is BFS. So without further delay, let's go into the topic. So this graph search algorithms, they are the systematically follow the edges of the graph. So we have for a graph, we have vertices and edges. So if you have a graph like this, let's say this is A node A or vertices A or B. So these are the edges or vertices, and this is the this is the node or the vertices, node A or node B, and this is the edge. Or if it is connected to node C, this is also the edge. Understood? So we systematically follow the edges of the graph to visit the vertices of the graph, and is used to discover the structure of the graph, whether it's a tree or it's a graph. And there are two popular algorithms for the graph search, which is breadth first search and depth first search. All right. So we'll go into details about deep depth first search. So over here we create a stack to keep a track of all the vertices. Stack means we can temporary storage of memory. Let's say you are storing node A, node B, node C like this. So this is a stack. It's a memory. So we create a stack to keep a track of vertices to visit. So we'll want to visit A, B, C. So we keep a stack of it. Then we choose the starting vertices, starting node, and push it onto the stack. Let's say we are starting with A, so we push it onto the stack. Next we want to visit B, so we put it onto the stack. Next C, SA. Are you understanding? While the stack is not empty, till the stack is filled, you do the following. So these are the algorithm steps. Check if vertices on the top of the stack have any unvisited adjacent vertices. If yes, push an unvisited adjacent vertices onto the stack. This I'll explain with an example. If no unvisited adjacent vertices or node, this is or node, are left from the current vertex, pop it on from the stack. Pop it means remove it from it. Okay. Repeat steps number 2 and 3 until stack is empty, which means all the vertices have been visited. So basically we have to visit all the vertices with some conditions. Is that okay? Now this is the basic algorithm steps. This is actually the pseudocode behind the depth first search. Okay, right now it's basically DFSG. G means V comma E. It will contain the vertices and the edges. Yes or no? So paint vertices white and attribute nil. Then check each vertices in V, and when a white vertex is found, visit it by calling DFC visit. So this is the algorithm background step. This I'm not explaining much in detail, but it's something to do with gray and black color. We'll talk about that, how to do it. Okay, so you can visit it, and I mean, let's say in a computer, if you want to implement this, we have to follow the steps, algorithm steps. All right. Now let's directly go into the example. Okay, so the pseudocode, what it does is it gives you the overview of the algorithm. Means it covers main steps of the algorithm. So this is G is equal G V comma E. So V is the set of nodes or vertices, and E is the set of edges, and G is the graph. All right. So these are covering the main, cover the main points of the algorithm or the overview of the algorithm. All right. Now directly we'll go to the DFS example number 1. This is my input graph. So please refer it, draw it please. So we need to identify. We need to start with the source node or the source vertex. So what is the source node over here which we consider? Will okay, you just write it down first. So over here, again we are writing it as graph is equal to v comma e. Then v is the set of vertices. That means v will contain a, b, c, d, e. That's it, right? It consists of 5 nodes. So what are we finding? I mean, what is the aim? What are we finding over here? In which order we should move ahead in DFS, depth first search, so that all the vertices are visited. Okay, our main goal is to find the discovery time and finish time of each vertices. So what is the main goal over here? To find discovery time and finish time of each node or vertices. Okay, are you understanding? So which type of graph is this? Is it a directed graph or undirected graph? It's a directed graph. Why? Because it has arrows. In this direction only we have to move in the direction of the arrows. Fine, understood the main goal to find the discovery time and the finish time associated with each node. So first we'll start with a source vertex, source node. So let's consider A to be a source node here. So this is my source node, source node. Okay. So what you do is you draw another graph like this right now. Because this is the basic graph. From here, how do we move ahead? We'll do it over here in the second graph itself. So I'll give you some time to draw it, the second graph. Again, the same graph again. Okay. So node A is a source node or source vertices or starting node, we can say. Drawn? Okay. So we'll go to the next slide. So we highlight this and mark it gray. White means they are not been visited. Gray means there was an algorithm steps na. Gray देखो, gray market paint white. See, gray. So here, what is this? This is the starting node, right? What is this one written over here? This is the discovery time. Discovery time. We start with one, or we can call it start time. All right. What I've written over here? One slash dash. Nothing is written over here. This is the finish time. We will write the finish time later. So one slash something. This is the finish time. So first we have discovered the node A, starting node. So this will come onto the stack. So draw a stack and mark A. That means we have visited node A. And we have written the discovery time as 1. 1 slash blank. This is step number 1. Now, from node A, where I can visit, I can go to node B. There are 3 adjacent vertices, right? From A, where I can go to B, I can go to D, and I can go to E. So you need to select one of them. Let's say we choose B. Let's say we choose B. There are 3 adjacent nodes. Now from A, we can go to B, we can go to D, and we can go to E. Let's select B, node B. So let us go to the next slide. So this, we have selected B. Okay. So the B ka discovery time will be 2 and slash dash. So B has come into the stack, right? Because we have visited B now. So write it like this, B. So put B in the stack. Why? Because we have visited B now. And the discovery time will be updated to 2 because there's a second node which we are visiting. All right. Basically, this stack is a last in first out stack data structure. Last in first out. You understand? Last in first out. Yeah. Understood up till now? We started with the source node, updated the start time as 1. Then there were 3 options to visit. We selected B, and B we have incremented the time as 2, the start time as 2. Now from B, where I can go? I can go either to C or to D. Again we have to select one. Let's say we selected D. Okay, so once we selected D, we'll write 3 slash, okay, and we update, put D onto the stack. So update it please. So put D into the stack because we have visited D node and we have incremented it to 3 slash 0. Now next, what from D, what do we do? D has 2 adjacent vertices, right? Where it can go to C or it can go to E. Okay. So now next will be, let's select that it goes to E. So E will come onto the stack. Up till now clear. And this start time will be, or the discovery time will be 4 because that's the 4th node. We're going incrementing by 1 1. Done. We are marking it gray because when we mark it black, when both start and finish time is there. So up till now clear. From E, where do we go? From E, we can go to only one place, B. There is only one place to go, B. Because B is already onto the stack. So we cannot visit. So B is already in stack. So we cannot visit B again. So it will go to node B, but it will do a backtrack. Okay. So we will go to node B, but we have to do a backtrack. It will go from B to E. So what is the first element, last element over here? Last element is E, right? E, right? So now what will happen is E. Now actually E should go to B, but B is already onto the stack. So what will happen is it will go back to E. Okay. So now B ka, we will not never visit E again now because it has come to E. Now E we are removing from the stack. Why we have to remove from the stack? Because we already visited B. We do a backtrack over here. See, like this. So now this has become black and we update the finish time to be 5. Understood? And we have removed this E from the stack. Why? Because that's the only one to remove. So when we remove something from the stack, if we have to update its finish time. So this is my finish time now. Are you understanding? Yes. So again I repeat from here. So from E we have to go to B. But B is already onto the stack. We cannot visit B again. So we do a backtrack. So it will go to node B, but it will do a backtrack. So job of node E is finished. Okay, that's why we make it black. So this 5 we update it over here. 5 5 because 4K but 5. So this is the finish time. So node A, node E or vertices E is removed from the stack. Uska job khatam. Now we go to node D. See what is on the stack? Node D. D and next. So D, how many places it has adjacent node E and C. Will it go to E? No, it has already visited E ka kam khatam. It will go to node C. So C will come onto the stack and this will become 6 slash dash. Understood? So from D it will go to C and C will be put onto the stack. See here. And this will be updated to 6. This is the discovery time. Means node C is discovered. When it was white, there was no start time, finish time. When it became gray, that means only start time. When it become black, start time, finish time both. Now what will happen? See, after C, node C has a cycle. Do you see that? Meaning node C, we cannot go back to D or B, right? Because see, it has a cycle. So what will happen? It is already visited, right? I mean, node C, it is the last in. It will be first two out. Now, again, it is going to node C. So what will happen now? It will go to node C, and node C is visited already. So it is finished now. So we remove this node C from the stack. How? By updating it 7. So here in the next step, this will be 7. Are you understanding? We cannot visit the node more than twice. So see how it is updated over here. So from here to here, because we are removing C from the stack. Removing means its job is finished. So from C, it will not come back to C again now. So we update the finish time 7. Understood now why 7? Finish time is 7 for node C. So check the top element over here. Top element was C. So it will go back to now D. So we have written the finish time to 7. Now from where, I mean, all the nodes are visited, right? But now what is element over here? D. So we have to go to D. Okay. So what will happen now? D will go to D. If you want to remove D, what will write over here? 8. Yes. So 8. Understood? We remove D from the stack. Now what is remaining? Top element is B, right? So we'll visit B. So here your finish time will be 9. Correct? Because you have to remove it from the stack. So now B will be removed from the stack. See over here. Alright. So B will be updated to 9. Yes, na? Now A is remaining, right? Now A has adjacent nodes. What? A has adjacent nodes B, D and E. All are finished their jobs. All have finished their job. For finally A is finished their job by writing updating over here 10. Yes or no? Now whenever it writes 10, it will remove itself from the stack. So update it to 10. So this is the last graph. This is the finalized depth first search graph. Now the stack is empty. Here stack is empty. We have visited all the nodes. We have assigned the start time and the finish time to all the nodes. Yes or no? All have become black. So the stack is empty. Now we can say DFC search is complete. And this is the final graph. You don't have to make black. What you can do is, in the exam, you can make it like this. You can write this, and you can slide with pencil. You can do this. This should be visited, na? So slide with pencil. What you can do is write 1, 10, and then use a very light color. That means it is visited. With pencil, you can just highlight it, or let it be. You're not writing a computer program, so you just write the notes. Alright, this should be correct. Understanding? Now this is an example. Just we'll do it together. Chalo. Let's do this. Try it on your own. I'll give you a minute. How to try it? Just check. It's easy, not so hard. Okay. Drawn? Now you can draw it on the same graph, no problem at all. What is the starting point? So this is my graph. Let us go it over here. This is my original graph. I want to maintain it. White means nothing, no start time, no fall time. So let us consider my starting node to be U. So I'll write 1 slash dash. This is my starting node. Node vertices, same thing. Starting vertices. And I've updated my, what is 1 over here? Discovery time. Okay. So from U, and I have uploaded U are visiting, na, to stack will be U. Okay. Fine. So from U, where I can go? From U, I can go to V. V, I can go to V or X. Let's say decide, let's go to V. So V will be 2 slash what? 2 slash dash. Okay. And update the stack with V. We have visited V. Up till now clear? So from V, where I can only go? I can only go to Y. No other option is there. Na? Backtrack is not available over here. So next option is I'll go to Y. So this will be 3 slash Y. Easy now. Next, where it will go? 3. Y. Y can only go to X. See here. So updated will be, stack will be updated with X. We have visited node X. So it will be 4 slash dash. Up till now clear. So ये सारे grey बन गए. Are you understanding? Now what do we do? From X, where it can go to V, but V is already visited. So what will happen now? Visit हो गया ना again. So what will happen? It will be revisited. Backtrack होगा. मतलब it will go back. It cannot visit node V again. So this will become red. So basically we are removing it from here now. So whenever we remove it, what will happen now? This will be updated with 5. Got it? So this is my finish time. Okay. Now what is the top stack now? Y, na? So we'll go to Y. So Y goes to X again, but X is already visited. So what will happen over here? It will go back to Y. So Y ka bhi time finish. So Y it will be 6. So Y is also gone from the stack. Sorry. Now where it will go? Now Y, from Y it will go to X, but is not allowed. So what is the next stack? V. So it will go to V. But यहाँ पे possible ही नहीं है ना. So it will end, we have to remove V also from the stack by updating it to 7. Correct? So V chala gaya. Next. From V, we can go to Y, but Y is already visited. So now see the next element, U. So we have to go to U. But this is not allowed, backtrack is not allowed, so U will be finished again. So U also remove from the stack. What? 8, right? So all this has become black. Now you will say stack is empty, but nodes have to be visited, na? So what will happen now? Let's go to W. Now we'll go to W. So stack will store now W. Okay, because we have to visit a node, right? Because it's not over, na? Let's visit W. So W will be, add W onto the stack, and what will happen over here? 9, na? 9 slash dash. I mean, let me write it uniformly in a black color. 9 slash dash. From W, where it can go to Y and Z. See here. Will it go to Y? So it will go to, so this will be 10 what? And it will be updated Z. Correct? Now from Z, where it will go? There is a cycle. So from Z it will visit Z only. So Z we have visited twice now. Once we have discovered and once we are leaving it. So Z will become, what will become over here? Black. We remove Z from this. Understanding? From the stack. Because it is visiting again. So this will be 11. Now what is left? W. So, I mean, next it cannot go to W. And backtrack not possible. So we'll go to W again. So to remove the W from the stack, we have to update this to 12. Now our stack is empty. Nothing is there. So whenever the stack is empty, my DFC search is complete. And see, the start time, end time, or the finish time, I have updated in all the nodes. So that means my example is complete. So imagine this coming in the exam. It will definitely come in the exam. but with a different graph, definitely. Understood this easy? Okay. So draw two graphs, one original, no, not now, in the exam, one original and one over here, so that we can see how the changes are done. Alright? And you have to keep on drawing the stack at every stage of time. Don't draw the graph again and again. Understood this? Easy it is? Yeah? So can we go to the next one now? Yeah. So we'll go to the next one now. I hope you have followed this. Just a minute. Okay, next I've kept in an extra graph from year to year. I mean, it's the same thing. Next is breadth first search. It is slightly different. Here we have to maintain a queue instead of a stack. Here we have to maintain a queue. See, you have to maintain a queue. Queue. Name notation as queue. Queue means this queue. So basically we need to create queue initially containing just the source vertices. Alright. And then again gray and again black. Black means all the nodes will be visited, but this time we have to store the information in a queue. Okay, so rather than explaining you all the algorithm, I mean if you want to implement this in computer, we have to feed in this algorithm. This is Q. Q means null. I mean Q, this phi means null matrix. The Q, no one is there in the Q. So this is it. Draw this. Once only draw it. So this uses a Q as a data structure. Q, notation Q as a data structure. Now in the next 10-15 minutes, we'll see how this works. You are ready? So this is basically, you know FIFO, first in, first out data structure. So that will be implemented in form of a queue. First in, first out data structure it follows. Breadth first search, BFS. And this is the queue which will maintain. So what is written in the queue? Source. So the source node is written over there. And we assign 0. So this is my source node. So that this means what? First in, first out means what? The first element entering queue will come out of queue first, right? Can you give a live example of that? First in, first out, railway ticket counter. You go first and you come out first, right? That's in railway ticket counter is a classic example of that. Correct, na? You stand in a line, whenever your turn comes, you're the first one, and you leave the first. You're the first person to leave. Okay. So let's discuss how this works. So all the nodes are given infinity over here, right? Infinite time to represent. This is given source. So this is my source node. Okay. So we have written this queue also as 0. We assign 0 to it. Okay. So the starting source node is S. So what are the vertices over here? It can go to V. This is an undirected graph. See? ठीक है ना? This is directed नहीं. There are no arrows. So it is an undirected graph. Alright. That's the difference. The DFS which we have searched, it was for directed graph. This is for undirected graph. And here all the weights of the nodes over here are given infinite time, first of all. So we have the three adjacent nodes. S can go to T, V and U. All the three nodes will appear onto the queue now. So S can go to what? Where? S can go to what? Come on. S can visit T, V and U. So all the three nodes you write it over here. T, U, V. So the distance of all of them will be 1, 1, 1. 0 ke baad 1, 1, 1. Correct? So this will become, see here, this will become 1, 1 and 1. You have written infinity over it. So you would have to write over here 1. This will be 1, 1 and 1. So the first element in the queue, 0 is gone because 0 we have visited, right? So now queue contains T, U, V. 1, 1, 1. So all three nodes appear na, from S, 1, 2, 3. So all three nodes appear. What is the distance? 1, 1 and 1. So they will be onto the queue. Now next. What's the first element in the queue? T. So T is visited first. Okay. So T is visited first means what? From T, where you can go now? You can go back to U, S or W. Yes or no? But U and V is already there over there. U to hai, so it will not go to U. So S is the source, SV nahi hai, so it will go to W. Okay, so W will be discovered now next. What will it a number? हाँ, ये first Q था, ये second Q है. So now it will be 2. Okay, and now what will happen? T will be removed because T से निकल गया. 1 assign हो गया ना. So what will be the Q now? U, V and W. 1, 1, 2. Understood? So W is denoted by 2 now. So next is, after you have gone to W, what is the next thing now? Next element is what? U. Alright. So what is the adjacent to U? V. So where all the nodes are visible now, T, S, S2 chala gaya, and V. All are visited. So it can be removed easily without discovering the new. But अब T, U ने कुछ नया discover नहीं किया. Okay. So the Q will be updated to V, W. 1, 2. Are you understanding? Then fifth. After what is the first element now? V. We'll go to V. V, देखो, W discovered है, S is gone, this. So सब discovered है, so its job is over. So it will remove it. So Q will be W2. समझ गए? Now we have in the Q W only with a weight of 2. From W we can go to X and Y. So what will be X and Y now? 3 and 3. Understood? So now step number 6 will be, Q will be what? W से, W का job है discover करना other nodes. So W has discovered X and Y. So this W will be gone. And what will be replaced? X, Y with 3 and 3. Already understood? So now what is the first element? X. Check for X. It's going back to W. It's going back to Y. It's going to Z. So Z will be discovered now. So Z will be what? 4. And X will be gone. So here it will have Y and Z. 3 and 4. Correct? Now from Y, We cannot go to W because W is already visited, X is already visited, Z is also already visited. So we remove it, simply Y. Now what is remaining? Z. Now Z is already visited, right? Now step number 9 में ये Q is empty. इसको बोलते हैं empty. So all the nodes are visited. Yes or no? Since all the nodes are visited, your DF, after this you'll come over here, your BFS is complete. Breadth first search is complete. Understood? This is how it will work. Easy it is. Not so hard. Easy it is. Alright? So here you have to maintain the queue and first element will be gone from that queue every time. First in, first out. Alright? Anything you want to write? All the steps have to explain. I mean, explain in the sense you have to update the queue. And all the numbers should be correct. So you don't draw with infinity, because you have to overwrite it. So you have to do it like this. So this will be 1 1 1, all discovered, then go to W. The W has discovered, so remove it from it. So X has discovered Z, so remove it from X. So Z is already discovered, Z cannot go to Y and Z, already discovered, so remove it from it. Q. Until the Q becomes empty, you keep on doing it until all the nodes are discovered. Okay? So can we see a fresh example now? I mean new example. So draw it. Draw this and then try to implement it. This is slightly at a higher level. But it works for undirected graph. Doesn't have a arrow. You draw it only once. I'll draw it twice. I have 2 times. See here also. I will require. And here Q will be given. I mean starting node will be assigned 0. Okay. So here what is the starting node? S, which is assigned 0. And the Q is S0. So whenever you do complete, let me know. Then I'll begin for the next part. Okay. Let us start now. So S can go to V U R. So it has discovered V U R. So that will become 1. So first Q will be, it has discovered, so it will be removed, right? S job is over. So it will discover R U V 1 1 1. Correct? From R U V R U V. We'll go to R now again. Yes or no? Or we'll discover R, right? R will discover what? W and T. Right? R, R. You go back to R because R has to be removed from here. So second step will be we remove R. But what do we add? See, W and T. So this will be 2. Correct? Overwriting is slightly difficult. This is 2. I hope you're understanding. This is 2. So what will be added? T, W, 2, 2. Okay. Now we'll go to U. U is the first element. Na? U से कुछ और discover हो रहा है? Yes. Y. So Y at the same time. This is at the same time. So Y is also will be 2. Why not 3? Y is 2. I'll explain why Y is 2. Right now you write it. So Y will be 2 and U will be removed. Why? Because you have discovered Y. So this Q will be updated like this. It will be V T, W and Y. This will be 2, 2, no, this will be 1, na? 1, 2, 2, 2. Now you might be wondering why Y is 2, right? I'll explain that. Wait. Thank you, Abhi aa gaya. So here we have first node as S. After node S, what it discovers? Check in the graph. R, U and V. R discovers what? W and T. W discovers and U discovers Y. Correct? W discovers what? W mein rakho. W discovers X and Z. Correct na? W discovers X and Z. So there are different levels of BFS. So see, this will be level 1. This will be level 2. So इनको 1 assign हुआ है. That's why we give it 2, 2 and 2. Now did you understand why we give Y as 2? And this will be level 3. Understood this? So these are 3 levels of BFS. That is why this is assigned 2, not 3. Now, what is the focus now? Now you have V. So V, where is V? V. Is V discovering anything new? No. So remove it. So now it will be T, W, Y. 2, 2, 2. Now we go to T. Go to T. Where is T? T. Are you discovering anything new? No. Correct, na? Already discovered, right? So remove T. What is left out? W and Y. You go to W. Is it discovering anything else? Yes. W discovering X and Z. So this will be 3. This will be 3. Understood why 3? Third level of hierarchy. See here, 3. So W is discovering what? So here I am going like this. See. Here I am going like this. And यहाँ से यहाँ पे जा रहा हूँ. ठीक है? वापस यहाँ पे लिख रहा हूँ Q. So W is gone because it has discovered what? X and Z. So this will be 2, 3, 3. Correct? Now we'll go to Y. Is Y discovering anything now? No, already everything is discovered. So Y removed. So we'll go to X and Z. 3, 3. Is X discovering anything new? No. So X gone. We have Y, Z. 3. Is Z discovering anything new? No. So this will be empty. Okay. And your, what we can say, this is your BFS tree. Or we can say breadth first search is complete. Easy it is. But only confusion will be that 2 wala part. So you need to take care of this hierarchy if you are confused. If there is one mistake, then that would have been 4 and 4. Wrong ho jata. It is in the same level. Easy it is. Yeah. So in today's lecture, we have discussed about depth first search and breadth first search. These two algorithms. So see to it that you practice their pseudocode also. Not necessary pseudocode. This examples will come in the exam. So just a revision. In breadth first search, what do we do? And maintain a stack. Here we maintain a stack. Yes or no? So whenever we discover any node, we put onto the stack. Yes or no? And why do we what do we remove from the stack? Whenever we remove, we update the finish time. Okay. Whereas in case of breadth first search, you can go back to algorithm. Algorithm will make sense now. Whereas in this step, what do? We maintain a queue. So we add we add the numbers assigned to the queue whenever they are discovered. And whenever we remove, what happens? We'll see whether that particular node has visited discovering other nodes or no. If it is not, we remove it. And the first element will be the first to get out. Is that okay? So this is all about, we have seen two examples of breadth first search and depth first search. So yeah, that's it for this lecture. Thank you.